Now I want to do something with my special triangles, and it's going to seem a little goofy at first, but I'm mostly just trying to prep for something that's coming next chapter. These are the ratios that we have for 30, 60, 90 and 45, 45, 90s. And we've got x's where that lets us be bigger or smaller. What I would like to do is I want this side to be 1. I don't want it to be x squared to 2. I want it to be a 1. And why do I want it to be a 1? I just do, for reasons that are coming soon. So we're just going to say, I want this thing to be a 1. Well, what can I do so that x is saying, hey, if you do the same thing to all the sides, like multiply or divide, you still get a good 45, 45, 90 right triangle. So I want to divide all of these sides for the 45, 45, 90 by x square roots of 2, because that's going to make this thing a 1, and that's what I want. Why do I want a 1? Don't worry about that for right now. Let's just say, hey, I want that to be a 1. But that means I have to do it to all the other sides. So I got to just divide this side by x squared to 2 and this side by x squared to 2. Okay, well that cancels these x's and we're left with 1 over the square root of 2. What I would also like to do is I got to rationalize my denominator. So I get the square root of 2 over 2. That seems familiar. We can do the same thing with this one. It's going to follow the same logic in progress. So we'll get square root of 2 over 2 again. Okay. Again, I want to do the same thing with 30, 60, 90s. I want to make my hypotenuse right here. I want to make that equal to 1 for reasons that are coming soon. Next chapter. So that 2x, I want to divide it by something to make it a 1. Well, that's easy. Divide it by itself. 2x. So let's divide all of these by 2x, because I got to do the same thing to all the sides. Here, these two x's cancel out, and we're left with the root 3 over 2. Man, that sounds familiar. Sure sounds familiar. What about this one right here? I'm just going to do it up to the side here. So we cancel our x's, and we're left with just 1/2. Man, that also sounds familiar. So I got these 1, square root of 2 over 2, 1/2 square root of 3 over 2. Man, that sounds familiar. So familiar. All right, now what we're going to do is I'm going to take those triangles, ones I had right here. I'm going to start with this green one over here. And I'm going to make it red, and I'm just going to draw it right on here. I'm going to plop that 45, 45, 90 right onto the Cartesian plane. 45, 45, 90. And this coordinate point up here, to make a coordinate point, you kind of go a direction in the x and a direction in the y. And you get square root of 2 over 2, square root of 2 over 2. Because that's how long this side is, square root of 2 over 2. And that's how long this side is, square root of 2 over 2. Look, we get square root of 2 over 2, square root of 2 over 2. The thing that those are coming from is that proof that we did. We did a proof that the sine of 45 degrees is the square root of 2 over 2. These don't have degree measures on there. So that coordinate point is spitting out cosine in the x spot and sine in the y spot. Oh, that must be neat. I wonder if that's unique to 45. It's not. Let's look at what happens if we take this 30, 60, 90. I'm going to take these side values and put them on the Cartesian plane and see what happens there. So here's that 30 degrees. I got the square root of 3 over 2 on the bottom, like I had just a minute ago, and then 1/2 on the side. Okay, coordinate point, the way that works is you have your x value going here, square root of 3 over 2, and your y value going here, 1/2. Look, we proved that the sine of 30 degrees is 1/2, and the cosine of 30 degrees is square root of 3 over 2. So if I draw an angle, I have that side length to be 1. Keep in mind, it only works if this is 1. If that's not 1, then this doesn't work. But the x value seems to be cosine, and the y value seems to be sine. How cool. Same thing happens with 60 degrees. If I kind of rotate that thing a little bit so that the 60 degrees is down here, then the cosine of 60 degrees, if I draw a 60-degree angle, that coordinate point, the x value, is the cosine value. But that is only if this thing is a 1. Same thing with sine. We get the square root of 3 over 2 for the sine of 60 degrees. Now you can see here I've been doing some goofy things with tangent. Tangent is, we did this in one of our homework problems, is sine over cosine. So a cool trick with tangent is it's sine divided by cosine. And we can see that right here. Square root of 3 over 2, square root of 3 over 2 divided by 1/2 gets us a square root of 3. And that was what was going on with those tangents, the other problems. Which is pretty neat. It's a very cool property. So we get this neat thing that the sine is always our y value divided by r, which is the hypotenuse. And I'm using r for the hypotenuse for reasons that you're going to see next chapter. Note here, down here at the bottom, there's a reason that there's a star here, that r is always positive. We're always going to have a positive value for r. Here it is. R has got to be greater than 1. So make sure you've got that. Our hypotenuse, we're always going to keep positive. Because now that we've drawn those angles, and now we're dealing with sine, cosine, and tangent, let's see what happens when we deal with coordinate points and we start doing sine, cosine, and tangent. See how that all works out.